Hi there, my name's Jason Harlow, and this is lesson 1 of a series of videos in an Introduction to Physics primer. I'm going to talk about physics for people who don't have a lot of background in physics but are planning on studying it. And it's all based on a textbook called College Physics, which is available for free on openstackscollege.org, so you can check that out. And if you open up chapter 1, this is what I'm going to be talking about today. So, first of all, what is physics? Well, another great source of free information is Wikipedia, which says that physics is the natural science that involves the study of matter and its motion through space and time, along with related concepts such as energy and force. More broadly, physics is the general analysis of nature conducted in order to understand how the universe behaves. So, water falls down, it refracts light so you can get rainbows. Hot air balloons will rise because of buoyancy force. Sometimes there will be a static discharge of electricity through the air in a thunderstorm. We have the sun, which is a star, and there's billions of other stars in the universe, which are organized into galaxies. All of these things are described basically by physics and the laws of physics, and that's what we'll study. So in your everyday life, physics has a lot of very important applications. If you use a microwave oven, that's got a lot of physics, which if you understand physics, you'll understand more about how it works, why you should not put metal in the microwave, maybe why microwave ovens might affect pacemakers. If you have a smartphone, or if you ever use any kind of a GPS mapping system to tell you how to get from one place to another, it's physics equations which determine the driving time between two locations on a map. So I want to go through a little bit of history. This is how the textbook starts. We're going to start with Aristotle, perhaps the first person to write down a lot of interesting physics theories. And Aristotle, so this is from 300 BC, he believed that every object in the universe had a proper natural place that was determined by what it was made of. And he divided everything into 4 elements: earth, water, air, and fire. And he felt that any object not in its proper place would strive to get there. So if you hold a stone up, a stone is made of earth. It wants to get back to earth, so it goes down. Whereas if you have fire and there's smoke above the fire, the natural place for smoke is up in the air, so it goes up. Galileo, in early 1600s, used experiments to replace or demolish or replace Aristotle's assertions. And he studied a lot about gravity and how things fall under gravitational influence. He found that objects of different weight all fall at the same rate, or if you drop them from the same height, it'll take the same amount of time to fall to the ground. And this is in the absence of air resistance. So we know that a hammer falls more quickly than a feather, but that's because of the air. And if you can imagine, as Galileo did, that maybe you could get rid of the air, like make a vacuum, then actually the hammer and the feather would fall at the same time. And whereas Aristotle felt that once an object reached its natural place, it would slow down and stop as being its natural state, Galileo felt the natural state of something could also be to be in motion. And it doesn't require any force to keep an object moving, as long as there's no friction. So these ideas of Galileo were expanded upon and modified by Isaac Newton, who wrote the Principia, which really laid the foundations for what we call classical mechanics today. So there's 3 laws of motion, which we'll study, and also the law of universal gravitation, which states that all massive objects attract one another. This is the force of gravity. And the story is that he was sitting out under a tree one day and thinking about the problem of what force keeps the moon in its orbit around the Earth. And then apparently an apple fell on his head, and that's when he realized that maybe the same force of gravity which pulls the apple down or towards the center of the Earth might also pull the moon down or towards the center of the Earth. So Newton's laws correctly predicted the moon's orbit around the Earth, also the Earth and the other planets and even the comets' orbits around the sun. So it was a very successful theory which lasted for about 300 years. Newton once said that if he saw far, it was by standing on the shoulders of giants. So the analogy here is just to keep in mind that the way we do science is we pay attention to and we have to learn about the previous contributions of other great scientists, and we build upon what they knew. So next is model. What is a model? Well, a model is a way that we understand something real. So an atom is real, but what we draw is this little cartoon image which shows what the nucleus is, which is a bunch of protons and neutrons. So there's blue balls and red balls representing protons and neutrons. And then these electrons, which are circles with a little minus sign in, because electrons are negatively charged, which orbit around the center. So this is a drawing of something that is real, but we can't see it with our eyes because it's too small. So this is a model. Another model would be a mathematical model where you take an equation. So here's an equation, y equals ax squared plus bx plus c. So, and there can be many, many different letters that we use. But in this model, what we've done is we've taken a and b and c are constants, which you can actually change. If you go to this interactive simulation, here's the web link for it. It's also on my webpage there. Play around with it. And if you change these constants, you'll get a different red line. And the red line is taking the variable x and inputting into this equation and getting an output or a prediction of a variable y. So x can change, and it gives you different values of y, and these constants a, b, and c determine what the shape of this line is. So there's something called the scientific method, and there's lots of different ways of describing it. I have my own personal sort of four-step method, which is, number one, you have to make careful observations of the world, ask good questions, and become familiar with what the trends are, what repeatable phenomena are, and what other people have done. So you need to become an expert in some area of science. That's step one. Step two is you use mathematical models like that equation, y equals ax squared plus bx plus c, theories which determine these equations, and generate some kind of a hypothesis and make predictions based on the hypothesis. Step three is perform experiments. Actually open your eyes, look at what the real world does, and try to design your experiment so that it tests your hypothesis and that you might be able to make an observation which would actually disprove your theory. And once you analyze your results, if what you see disagrees with your prediction, then you should change your hypothesis, change your theories. You may have to refine your theories based on what you're seeing and come up with new questions. And as you're doing this, you should publish and let other scientists know what you're doing. That's kind of a breakdown of a basic scientific method. Okay, so when you measure things, you need units. So physical quantities can be specified in terms of units, which are standardized values. So if you didn't have standardized units, it would be difficult for scientists to express and compare measured values with each other in some meaningful way. So here someone's drawn a map, and someone's said, oh, well, here's the scale. One cable is this long on the map. But there's somebody else reading it thinking, wait, what's a cable? So whoever made the map came up with their own unit of distance. So it's not very useful. So we have standardized units here on Earth. Most scientists use Système International, SI units. So length, you could measure length in cables, or you could measure it in miles or feet or inches, but the SI unit of length is called the meter. Okay? Similarly, mass, the SI unit is kilogram. I guess you could use grams, but for some reason the SI unit is kilogram, 1,000 grams. Time, the SI unit is the second. And for electric current, which you'll learn about in your course, your physics course, is measured in amperes. That's another fundamental SI unit. And all other physical quantities can be expressed as algebraic combinations of this length, mass, time, and current. So even charge would be the current multiplied by the time. So that would give you units of coulombs. So all these other, coulomb would be a derived unit then, ampere times a second. So let's give it a try. So sometimes in my videos I'll ask you to actually pause the video and answer a multiple choice question, A, B, C, D, or E. So here's the question. A football field has a length of L equals 100 meters and a width of W equals 60 meters. The equation for area is A equals L times W, LW. What is the area of the football field? And we know 100 times 60 is 6,000, but what are the units there? So I'll give you a moment to think about it. Please press pause, and when you're ready, press play. Okay, so hopefully you answered D. The area is 6,000 meters squared. So what you would do there, L times W is 100 meters times 60 meters. That's 6,000. And the units are meters multiplied by meters. And meters times meters is meters squared. So meters squared is the SI unit of area. Okay, so let's look at the other fundamental units. We've got the second. How do we actually define a second? It turns out that there's a certain type of vibration of cesium atoms that you can measure using an atomic clock. And we define the second to be this 9 billion of these vibrations. There's the actual number, 9,192,000,000, etc. And that's what gives us the second. Light travels a distance of 1 meter in this many seconds, so it's some fraction of a second. So the distance meter is actually determined as being distance as speed multiplied by time. Once we've defined the second and we know the speed of light in a vacuum, we can figure out what a meter is. And the kilogram is actually based on an actual hunk of platinum iridium that is sitting in a vault in Paris, the Bureau of Weights and Measures near Paris. And there are exact replicas of this standard kilogram, which are in different labs around the world. And every once in a while, someone takes it out and weighs it and compares it to other standards so that we all agree what a kilogram is. Now, sometimes you may not want to use a meter. You might want to use longer lengths. Kilometers is 10 to the 3 kilogram, or kilogram is 10 to the 3 grams. Centi is 10 to the minus 2, that's a hundredth. So each power of 10 in the metric system represents a different, what's called order of magnitude, different power of 10. And here are some common prefixes that you sometimes see. 10 to the minus 6, or a millionth, is the symbol there is micro, and that's a mu. So, for example, 0.01 meters. Okay, that's a hundredth of a meter, or 10 to the minus 2 meters. You can call that 1 centimeter. So often you need to convert from one type of unit to another. This is the last thing we'll do today. For example, let's convert 80 meters into kilometers. What you need, or a good way of doing this, is to multiply by a conversion factor. A conversion factor is a ratio that's equal to 1, which you form by taking one unit and dividing it by another. For example, we know there's 1,000 meters is the same as 1 kilometer. So we can set up a ratio, 1 kilometer divided by 1,000 meters equals 1, so we can multiply that. And if we set it up right, if we want to convert from meters to kilometers, we put the conversion factor so that meters is on the bottom. That way, meters here on the top cancels with meters on the bottom. You just end up with units kilometers. So 80 times 1 divided by 1,000 is 0.08. So 80 meters is 0.08 kilometers. So why don't you try it? Again, you can pause this and I'll tell you the answer. If you know your height in inches, say 65 inches, and you want to convert it to centimeters, you can use the fact that 2.54 centimeters is the same as 1 inch. So if you're going to multiply this 65, would you multiply it by 2.54 divided by 1, or would you multiply it by 1 divided by 2.54? I'll give you a moment to think about that. Okay, so hopefully you answered A. The idea here is that inches is on the top for 65, so you set up the ratio so that inches is on the bottom. That way inches cancels with inches, and you get centimeters. And what you plug into your calculator is 65 times 2.54 divided by 1, and you get 165. And that sort of makes sense.